Infinity. This is a talk about infinity. And I wasn't sure what the audience makeup was, but I know most of you here. So first question, are there any math students in here? No? Just one? Just you? Okay. All right. Well, so then if you're watching this online, it'll be less interactive for you. But so this talk is basically about infinity, and the purpose is to bring it down to kind of a general audience, but there may be some parts which are a little more mathematical for the math students. Since there's only one that I know of in here, we may spend less time on that. Okay, so the first question is, what is infinity? All right, that's the first question we want to ask. And so the thing about mathematics is about definition. You cannot use like kind of layperson dinner conversation definitions about things, meanings about things. You actually need a formal mathematical definition when you talk about concepts. Okay, so one question I wanted to ask just the audience, I'm curious, it's not to embarrass you, it's just I just want to know what you think infinity is. We all learn about infinity when we were kids. We ask our mom or dad, like, what's the biggest number? Right? And they'll say, oh, infinity. Like, but is there anything beyond that you guys think of infinity? Like, if someone says, what's infinity, what is it? I'm just curious. An abstract concept. Okay, that does not help. Yes, it is. Yeah, I'm joking. There's going to be some comedy here, so math isn't that boring. Yeah, so it is abstract, but what does it mean to you? Yeah, what is it? Something that goes on forever. Yeah, that's something that keeps going, right? Yeah, I've also heard the biggest number. Anything else? Anyone heard anything else? Infinity? Yeah, no bound. It's unbounded, right? That's another one. It's no boundary. Okay, right. So those are definitions which are fun to use in casual conversation, or if you're in college hanging out 3 in the morning with friends in a dorm room, you want to kind of act like you're philosophical. You talk about those things, but you don't really know what they mean. When you know what something means when you've defined it properly, and that's what happens in mathematics. So before you can talk about infinity, you have to talk about what is a number. In mathematics, you have to know what a number is. What's the definition of a number? And even that's a hard question. Those of you who studied Nahu at here, Darul Qasim, or anywhere else, you've gone through these kind of issues. Like, how do you define what a word is? We all know what a word is, right? But how do you define it? Right? That's not a trivial definition. And so the same thing with a number. If I ask you what a number is, that's also not so trivial, but we all know what it is. All right, and so we can ask the following. You can ask the question like, what is 3? What does the number 3 mean to you? Okay, anyone? I'm curious just what you think. What is this? If I say 3, what is it? What comes to mind? What do you think of? What? That's a number. Well, what though? You've got to think of something. There's an image that comes to mind. Yeah, 3 something. Like I used to think of oranges when I think of oranges. Like, oh, give me 3 oranges. If I want to tell someone, give me so many oranges, I'll ask them for a number. Right? So this is usually what you think, and that's what you think as a kid. Like you just confident, yeah, I know what 3 is, I know what the meaning is. But what it really is it's this collection of 3 objects. Right? It's a collection of objects which you in your mind have associated with the number 3. And so as a mathematician, I could make this much more formal and say, well, it's going to be this kind of set bracket, these curly braces, and then instead of 3 oranges, I'm going to put this letter A, this letter B, and this letter C. Right? That would be my set. It's the same as the oranges, right? Okay, so what you can then say is, well, a number like 3 or 7 or 8 or a million, these numbers are basically the sizes of a set, right? And so the set is really the number, and 3 is a symbol that we give to talk about the size of it, how many are in it. And we've all agreed that 3 means this number of elements. Okay, but now there's a problem. What is it? From a mathematician's point of view, there's a problem. What? Yeah, that's one. That's actually more advanced. But even more simple than that, what is it? What? Someone else say something? Yes, very good. What is a set? Now we've used a word called set, and we don't have a definition for it. We need a definition, right? And this is where the definitions stop. So what is a set, right? So the set is a collection of distinct objects, and an object is anything. An object is absolute. There's no restriction on what an object is, right? So now we've reached the end of definitions because an object is just anything. Right, so what is a set? It's a collection of distinct objects. Right, so here's a set. Zayd and Amr. We're at Darul Qasim. If you study Arabic, Zayd and Amr comes up always. Zayd hits Amr, right? Zayd steals a pen from Amr. In your Nahu, your grammar, even Sarf, I guess it'll come up. But regardless, this is a set of 2 elements, Zayd and Amr, just 2. All right, here's another set. Attendees of this talk, all right, just the physical attendees. If we take all of you, your names, who you are, your person, and we put them in a collection together and say make that collection an abstract collection, then that would be a set, right? Here's another one. How about all the planets in our solar system? How many are there now? 15? 14, 15, so it used to be 9. That was when it was easy. Hundreds? Oh, great. Okay, so it's some large number, a relatively large number. Right, that's another set. Here's another set, stars in the universe. Okay. Physicists believe this is finite, but there's also some theories that maybe it's more than that, maybe infinite. How about fruits in Mexico? That's a lot of fruits in Mexico. So those are all sets. A set can be pretty much anything. It can actually get a lot wackier than this, but you can only understand those when you start doing formal mathematics. But in kind of regular life, day-to-day life, these sets work just fine. Okay, so now what is the meaning of the number 7? So to a mathematician, the number 7 actually has somewhat a concrete meaning. We say this. Well, let's take a set with these elements, these objects, okay, U, M, T, W, R, F, S, and we'll say that this number 7 is the size of that set. That's what we'll define. It's the size. It's like that set itself. Anyone know what those stand for? Those letters? Yeah, days of the week, right? U is used for Sunday to distinguish Saturday. So they actually have meanings. We're using them as letters, whatever, it's a set. Okay, so are we good with the definition of a number? No, we're not. There's a problem. This is actually this is insufficient. Why? You had mentioned, we have one math student here, so he mentioned it. What was the problem? That's right. If we say that's 7, what if someone else comes and says, no, they have another set of 7 elements. They could choose something other than these letters. They can choose whatever they want, different types of fruits, animals, people, whatever. All right, and so let's just look at the number 3. At the number 3, I could come and say, okay, here's my set of 3 elements. It's A, B, and C. These 3 letters. Okay, that's my set. Then someone else can come and say, no, my set is Zayd, this person Zayd, Amr, and Hind. Hind is a girl's name. So the progressive Muslims are happy. We've mixed the men and the women in the same set. A little more excited. Tough crowd, 9:30 in the morning, man, tough crowd. All right, so you have 3. That's a set of 3. That's a set of 3. That's another set of 3. That's what our audience member said. Here's another one. Someone could come and say, okay, I'm thinking of this set. It's a piece of cantaloupe, an egg, and a Fatima bread hot dog. All right, so we have 3 elements again here, which you could say is 3. So now this number 3 points to all 3 of these sets. So now we have a problem. And mathematically, you can't say, oh, 3 is just this set, because someone could have a different set. So we need a way to say that those 3 sets are what? We want to say that they're the same, right? We want to say these 3 sets are the same. So you have to do that mathematically, because in mathematics, those 3 sets are actually different sets. They're not the same. Okay, so the solution to that problem is something like this. You want to set up a mapping where you can say that these 2 sets are the same. And we need to introduce this concept in math called functions. Okay, so I think most of you have gone through high school. I hope all of you have gone. We have a 16-year-old age limit here. So most of you have gone through high school. Oh, 2 violators right there. But his father's here, their father's there. It's fine. All right, so you have, in mathematics, you have functions. Functions have this thing called a domain and a range. You map things together, right? Okay, so without going into the details too much, we can still work with pictures. So in a function, basically, you want to say, I want to associate each element of this one set A, B, and C with the set cantaloupe, egg, and hot dog, right? And so if we can do that, then we can kind of say they're equal. So the way you do it abstractly is, or more formally, you say is that you give letters to these. So you give names. So you say the set ABC is actually called X. We're going to label it X. And the other set we're going to call Y. This comes after X. So we have X and Y are the 2 sets. Okay? Now, a function is what it's written like this. Is a function, we'll use the letter F. On the left side will be the source set, which is the domain. This is the source. And on the right side is what's called the range. It's where the mapping is happening to. So we're going to map values from X to Y, and we'll just line them up like this. It'll look easier. So what we can do for this function is we have to define where each one of these elements goes. Okay, so we can do it just like this. We can say, well, we'll map A to the cantaloupe, B to the egg, and C to the hot dog. Okay, so now the 2 sets have this mapping set up between them. All right, I could have done this way. Could have done this way. A goes to the egg, B goes to the cantaloupe, and then C goes to the hot dog. You can do it any way you want, right? You can do this too. You can say, well, I'm going to send A to the cantaloupe. I'm going to send B and C to the hot dog. So what's different about this? What is it? Anyone? Yeah, 2 elements on the left side are now mapping to the same element on the right side. So that's different from the other 2. The other 2, you had distinct mappings on each one of them. Okay, so so first we need to introduce a couple definitions. So don't get bogged down too much by the I guess the cryptiness of this. Just it'll be straightforward with the pictures, but we say a function f is called an injection. It's injective. It's an injection if the following happens. Distinct objects in x, if you have different objects in x, they're going to go to different objects in y. That's when we call a function an injection. So it's a mathematical term. The other term is called one-to-one. It's a simpler term that's used. Okay. And so if we look at this, is this an injection? Yes or no? Yes, it is. Different values, a, b, and c, different values there are going to different values on the right. So that is an injection. How about this one? Injection? Yes, it is. Because A is going to egg and B is going to candle. They're different values. Even though they're crossed over, they're still different values, just different order. How about this one? Injection? No, it's not. Because now A, B, and C are two different values in X, but they're going to the same value in Y. Right? Okay, and then one more that we need, one more definition is called surjection. A surjection, a function is called surjective, or it's a surjection if what? If every object in Y is hit by something in X. Okay, did you actually hit everything in Y on the right side? So if we go here, this is an injection. Is it a surjection? Are we hitting everything in Y? Yes, we are. We've hit the cantaloupe, we've hit the egg, and we've hit the hot dog. So they are, all three have been hit. Okay, so that's surjection. How about this one? It's an injection. Is it a surjection? Yes, it is. You've hit everything on the right side also. Okay, and then finally our failure will be this guy. This guy failed to hit the egg. Right, so this is not a surjection. All right, and then the last definition is bijection. We say a function is a bijection if it's both an injection and a surjection. Okay? And if you think about what that means, it'll take some thought. This is like where you're driving in your car, kind of spacing out, traffic light, and then you think about these things. Eventually you'll realize that if you're an injection and a surjection, what that means is the two sets x and y are actually in correspondence with each other. Every element of x and every element of y can kind of be paired together, and so you can kind of say that they're kind of married together. They're almost the same set if you try and count them. Okay, and so this is an injection and it's a surjection, so therefore it's a bijection. This set was injection, surjection, so it's also a bijection. And this one is not a bijection. This function is not a bijection. Okay, so why does this matter? Why are we doing this? Why do we need this machinery? It's because we want to understand what the size of a set is. Right? The size of a set. And the basic conclusion we come to is, and this is actually a definition, we say two sets x and y are said to have the same size. What does it mean for two sets to have the same size? Well, as your child of understanding, you would say, well, I'll just count the ones on the left and I'll count the ones on the right. And if they're the same number, they have the same size. But later you'll find that that doesn't work. That doesn't work when you start getting into larger things. But for these things it works. For these things it works. But for this definition will work for everything. So we say two sets x and y are the same size if you can find a bijection between them. Okay? If I can find a way to pair them up so that each element corresponds to exactly one element on the other side on x and y, then they have the same size. There's a bijection between them. Okay? Okay. Any questions about this? No? All right. So finally, because of that, we can look at this and say, well, that number 3, it doesn't matter which set you pick, because all three of these have bijections between them. So mathematically, they're all equivalent. So we say now we have a definition for the number 3. It's this kind of quantity. Right? It doesn't matter what objects you actually pick in that set. Okay? So because you can do this, why do we want to use hot dogs and eggs, cantaloupes, A's, B's, and C's? Why don't we standardize what a set of size 3 looks like? Right? And so that's where we get to something called the finite sets. These are all the numbers that you've ever known your whole life, finite. This talks about infinity. We'll get there, but everything we know up till now is really, that we know well, is finite numbers. Right? So what mathematicians did was they just gave labels to them. They said, let's take the set of just one element, and we're going to give it this label 1. Okay, that digit 1. And the set is going to contain not a hot dog, not a cantaloupe, not the letter A, not Z. It's going to contain that symbol 1, which is pretty. It's like the same number that's used for the size is going to be used as the element. But how do you define the number 2? Anyone? 2 ones, but then the ones are identical. We need distinct objects. Good guess. 1 and 2. Yes, that'll work. We can say 1 and 2. Now you can say the number 2 is 1 and 2, the set 1 and 2. Okay? And then 3 is like this, and 4 is like this. So now we have numbers. We have finite sets and finite numbers. If we want to look at the number 100, it's 1, 2, 3, comma, all the way up to 100. Okay? And so we call these finite sets. These sets are the finite sets. Anything of this form is a finite set. Okay? And then they give rise to the finite numbers. Those are finite numbers. Does it make sense? Okay, so this is the formal definition of 1, 2, 3, 4, 5. Are there any computer science people, software engineers in here? No? 1? Wow, thin crowd, thin science crowd. Any scientists here? Science? Bachelors in biology, chemistry, physics? You're all artsy people? Wow. Okay, that's good. So from computer science, you should know your science. Your science. Your deep science. All right, so from this, at least a scientist or a computer scientist, you may have seen something. There's this kind of recursive process here, right? You can go to the number 2 and say it's actually the number 1 plus 1 element, and then 3 is like 2 plus 1 element. So you have like a sense of recursion, and even mathematically, that's how it's done in formal mathematics. Looks a lot uglier than this. Is a pretty form of it, but anyway, that's what it is. Okay, so now finally on to infinite sets. So if we want to understand infinity, you have to understand what an infinite set is. Okay, so what's an infinite set? And we have enough math now, based on these previous slides, to actually give a definition. A set is infinite if it admits, a set is infinite if it admits no bijection with any finite set. Okay, so a set, you give me a collection, I'll say that's infinite if you cannot find any finite set that this thing has a bijection to. If no such bijection exists, then we say it's infinite. Okay, so what's an example of an infinite set? So I'll give you the one that everyone knows. All the counting numbers. Take the set of all the counting numbers. What are the counting numbers? 1, 2, 3, 4, 5, and on. Right? And so it's this set over here. And the dot, 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 the ellipsis means just keeps going on. These are the counting numbers. They're an infinite set. There's a mathematical term for this, actually. Well, before that, we can also put them on the number line. When you draw a number line for your children, for example, the first time you see it, you'll see 1, 2. These are dots on the line. And it continues to go on and on and on with an arrow on the right side. And they're actually called in mathematics the natural numbers. That's the formal term. It's called natural numbers, and it's given the number n. Counting numbers are n. Okay? So is this infinite or finite? This is infinite, right? What if you took one of the finite sets and tried to create a bijection? What would happen with this? So you could line, let's say, the size of elements of size 6, 1, 2, 3, 4, 5, 6 on the left side, and then we'll put the natural numbers on the right side. Okay? Now, if you try and set up a mapping, you're going to map 1 to something, 2 to something, 3. I just put them in order like this. Right? But what happens then? Eventually, you're going to run out. You're not going to have enough because the ones on the left stop. Right? You could have, so these get left out, and it didn't matter what order you could have done, kind of any order. Those will always be left out. Okay, so finally we have a definition of infinity now. We didn't actually define infinity. We defined infinite sets. What is infinity to a mathematician? This is one definition. It is the size of an infinite set. That's it. So remember, the number 5 was the size of that set with those 5 elements, A, B, C, D, E, right, or 1, 2, 3, 4, 5. Infinity now, to a mathematician, is the numbers, the size. It's the quantity you give to the size of an infinite set. So it's still going to be abstract. It takes a while for these things to sink in. It takes a lot of coursework and stuff. But anyway, that's the definition. Okay, so, right. We're going to need one more thing. We showed how the finite sets were always smaller than infinity. When we took the numbers 1 through 6 and showed that you couldn't map it, But we did do something with that 1 through 6 to the natural numbers. We created a function. The function wasn't a surjection. It didn't hit everything on the right side. But was it an injection? Were different numbers going to different things on the right side? Yes, they were. 1, 2, 3, 4, 5, 6 still went to 1, 2, 3, 4, 5, 6. They went to different values. So what we say mathematically is that if you have two sets x and y, and if there's an injection from x to y, meaning you can find a home for everything in x in y, a nice home for it, but you don't necessarily hit everything in y, then we say x is actually less than or equal to y. Okay, that's the definition of it. X is less than or equal to y. All right. Another way is you can say x is not bigger than y. All right. So if you take these two sets, for example, x and y, is x less than or equal to y here? Yeah, it is, and it seems pretty obvious, right? We don't need that injection stuff, but you'll need it when you get to infinities. So let's look at these just quickly. Let's do the injection. So how does the injection work here? If I have 1, 2, 3, 4, 5, can I create an injection from x to y? Can we do that? So how do you do it? Line them up, and then what do we do? Yeah, map. We can send 1 to 1, send 2 to 2, send 3 to 3. Okay, that's it. It's an injection. It's not a surjection. It doesn't cover everything. It's not a bijection. We know they're different, 3 and 5. They're not equal. But at least we can say x is less than or equal to 5. And you could have done this in any order. You could have picked any order you want. Like, this is another function. You can map them this way. So it's still an injection. So because of that, we say x is less than or equal to y. Can we say the other way around? What if we flipped the roles of x and y and said x was this one and y is this one? Can you inject x into y now? You can? How? You could set 1 to 1, 2 to 2, 3 to 3, but what are you going to do with 4 and 5? You can't send them to 1, 2, 3 because this is an injection. You can't send two things to the same value. So we can't send them to 1, 2, 3. So because of this, we can say that y is less than equal to x, but we can't say x is less than equal to y in this case. Right? Does it make sense? Does it make sense? So the finite sets are kind of easy to deal with. Right? Now let's go to the size of infinite sets. And this is where things get interesting. All right. Okay, let's take the natural numbers n. That's an infinite set. It's not finite. There's no bijection between this and any finite set. How about this set, y? What's the difference between y and the natural numbers? There's no number 1. Yes. We removed 1 from the natural numbers. So now it's left with 2, 3, 4, 5, 6. Is y infinite? Yes, it is. Okay, so now question for you. Question. Can we say n is less than or equal to y? N is equal to y? Y less than or equal to n? They're both infinite? Ah. But what about what about the mathematical definition? So that's a good point. Yeah, that's a very good point. Akbar says this point, they're both infinite. And that's how we think. Without mathematics, that's what you would think. They're both infinite, so... Oh, wait, so I'm sorry. Is your answer that they're both equal? They're both equal. Okay, so they're both infinite, so they're both equal. Right? That's a very natural, kind of a natural opinion. And so let's see. Can you do that? Well, from a mathematical point of view, how do you show two things are equal now? We have to create a bijection between them. Can you find a mapping from one to the other where every point is covered on the bottom side on y, and any 2 points in n are going to go to 2 different points in y? Can you do that? How do you do it? Why? Because you're short by 1? Yeah? You have to what? You're short 1, that's what Rafi was saying. Yeah, you're short by 1, right? Well, check this out. Just do this. We can map 1 to 2, 2 to 3, 3 to 4, 4 to 5, and just do this all the way through. So if you wanted in like a mathematical form, you can say, I'm going to map the number I to I plus 1 in the other one. That would be the functional form. What have you done with this function? You have created a function from n to y. Is it injective? Are 2 different values in x going to 2 different values in y? They aren't? Which ones aren't going to 2 different values? If I look at values 3 and 4 in n, where are they going to? 4 and 5. Those are 2 different values. So they are. There's no 2 arrows going to the same one. So this is an injection. Is it surjection? Is it a surjection? Are we hitting everything in the second set? Yes. If you take any number in the second set, you give me 999. Then which number mapped to it from n? 998. Exactly right. Right? So 1 less. So this is a bijection between the two. And so it's fascinating in the world of infinities, these are actually the same. These 2 numbers, I've taken away 1 element from y, or from n, and it's actually the same size as n. Okay? All right. How about this one? Okay. So the natural numbers are 1, 2, 3, 4, 5. What's the second one called? Anyone know? The negative numbers, but the whole thing with negatives and positives, there's a term for it. Integers, right. In fact, the number is actually, the letter z is given to integers. But I accidentally put I and then realized it later. But I thought maybe I is easier because Z is kind of confusing. But Z, I think it's some German, the German root is why it stands for the integers. I forget. But we're going to call it I for integers. So I is infinite, right? It's not finite. There's no bijection between I and a finite set. The question is, how do you compare n and I? Because n keeps shooting off in one direction to infinity. What about I? Shoots off in both directions, right? They're both infinite. So what do you think? In fact, we can even put them on a number line, make it a little prettier. So when your children get to 4th grade, 3rd grade, 4th grade, 5th grade, they start doing negative numbers. On the top, they'll do like the natural numbers 1, 2, 3, 4, 5, and the arrow goes to the right. Then you show them the negative numbers. There's like 0, -1, -2 to the left. You put them on 2 number lines. And so, but we can remove those. The question I have is like, what do you think about the sizes of these? Is one of these bigger than the other? No? You think they're the same? Same argument as Akbar Kif? Infinity is infinity? Okay. What? Second one's bigger? I is bigger? It looks like it's bigger. Yeah, it's like it's going longer. Right? It's okay. So remember, if you want to say they're equal or less than or equal, you have to find injections or bijections. So can you find an injection from n to I? Can we inject n into I? Yeah, we do. It's 1, 2, 3, 4. We know what its definition is. What is that? Oh, no, they're distinct elements. They're distinct elements. So I can take that 1 and I can map it to 1. I can take 2 and map it to 2, 3 and map it to 3, 4, 4. So n is definitely less than or equal to I. I can fit n inside I. It's an injection. That would be my injection. The question is, can you do it as a surjection? Can you create a bijection between these two? Other than Eunice, anyone have an idea? Do it. How? You can. You can actually create a bijection between these two so that every single number gets hit by drawing lines. Anyone see it? No? All right, okay. What do you think? Yeah. That's right. So you can start with the number 1 and send it to 0, and then you can take the other ones and keep flipping back and forth which way you go. All right, I'll show you in a picture. It's easier. So what you do is this. You order them this way. So n is the natural numbers. Then the integers, just order them this way. Start with 0, and then do 1, -1, 2, -2, 3, -3, 4, -4, like this. And then set up the mapping this way. And there you have it. So now the naturals are mapping into the integers. Is it injective? Yes. Any two different natural numbers is going to two different integers, right? They're all going to different ones. You can even create a formula if you want for this, but it's easier in pictures. And then are we going to hit every single integer this way? Yes, we will. You keep going. So they are in fact the same. So these two are in fact the same, right? And so mathematicians knew this. They knew this for over 2,000 years. The Greeks knew this about infinities. Indians and Chinese always claimed that they knew it, and eventually you find out they did, separately, independently, that 2,000 years ago someone said that there's these infinite quantities, this and that, in numbers. Right? In fact, you can go even one more level to make things really fun. You have that was sarcastic for non-mathematicians. Products of sets. You can actually take the products of sets, which you know, if in elementary school, you remember 3 times 4? What's 3 times 4? What is it? 12, yes. 3 times 4 is 12, right? But if you ever think about it from a mathematical point of view, we said 3 and 4 were these two sets, right? How do you take the product of two numbers in sets? What you do is you turn one of them sideways and you make this rectangle out of them. And this is really where 3 by 4 came from, 3 times 4. You know, and you just put coordinates on each left and right possible coordinate between them. So it's like 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, like a grid. And then you count those dots and you get 12. And in the British system of numbers and times tables, it went to the subcontinent. They say 3 4s are, right? 3 4s are 12, all right? Because there's 3 rows of 4 in there, 3 times 4. Okay, so that's 3 times 4. You take two numbers, you can multiply them. But we can do something more now. What is n times n? What was n? It was the natural numbers. Because we have sets, we can actually multiply. We can take a product of them together. And so you do the same kind of thing. It looks, if there was more mathematicians in the or students, math students, I would have asked you guys, but it's only one. So, so here's n. This is how the natural numbers look. Let's just get the thing without the numbers on it, just the dots. If I wanted to multiply it by itself, n times n, what do? So you put one of them vertically, you put one of them horizontally, and then you fill in the grid of fill in the grid. So n by itself on the top is just this long set of points. The n by n, when you do, it's actually it's even called n squared. N cross n, n squared, n product with itself looks like this. It's an infinite rectangle, right? And it's even more fascinating because look at the rows of n cross n. Each one of them is a copy of what? N itself. So you basically have a copy of n, then another copy of n, okay? And how many of those copies do you have? N of them, yeah, very good. You have n. You have infinite copies of n itself. So you get this big grid, n squared. And similarly, you can do n cubed and n to the 4th and make 3-dimensional, 4-dimensional, right? So question again to you. What's the comparison between these sizes? Is n cross n bigger than n? Or is it the same? You think it's the same? If you think it's the same, you have to find a bijection. Can you find a home for everything in n cross n in n? Can you map n into n cross n so that you hit every single point? Because that n lives as each row. So I could exhaust an entire row with just n, and I have all these other rows left over. But is there a way to do it that you actually hit everything? You see it? It's really hard to see, actually. So what do you do? So here's how you do it. You take the first element in n, that would be like the number 1, and you map it to the lowest left corner, 1, 1, all the way to the bottom. So now I've taken care of 1 point. All right. Good job, shabash. Now, take the next two, this is the key step. Take the next two numbers and map them to this diagonal down here, these two on the diagonal. Okay? Now I've taken care of 3 points. And then what do I do? What's the next step? Anyone? Where? Diagonally 3, exactly right, like this. Now the next three numbers, I can put 3 like this, right? And I can do 4 and 5, keep going. And am I ever going to run out? No. I have enough numbers in n to map to all the numbers in n cross n, like this. And you can even do it formulaically where they are, but that's it. So eventually you cover everything. So that's your bijection between n and n cross n. So again, another fascinating fact, I found this fascinating when I was a math student. Well, n and n cross n have the exact same sizes, both of them. For the math students, there may be some math students online watching this, but n cross n is actually something a little special. If you imagine the numerators and denominators of fractions, then n cross n is actually these fractions. 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, then 1 half, 2 halves, 3 halves, 4 halves, 1/3, 2/3, 3/3, 4. So what you're actually showing when you say n cross n is the same as n, n cross n are actually the rational numbers. All the fractions, the rational numbers, have the exact same size as the counting numbers, 1, 2, 3, 4. They're the same infinities, both of them. Okay? So finally, that was it for like showing you infinities that are same. So like I said, mathematicians knew this for a while, for over 2,000 years at least, they've known this. And who knows who was doing what in their own cave or in their corner, in their home. You know, you never know what people were doing because there was no internet, no communication back then. It was very difficult for one mathematician to talk to another mathematician, and then for them to even get out to the open. In fact, it was probably very easy to steal someone's work because you could just go meet someone, get their, learn from them, and then go pawn it off as your own. It was pretty easy back then. It's a lot harder to do now. Sure, it happens, but it's a lot harder. So George Cantor was a German mathematician for over 70 years, 1845 to 1918. He was the first to actually find something that was different from what mathematicians have done with infinity for a while. Okay, and so I'll show you two sets now that he studied. One was the natural numbers everyone knows, and then there's other set called C. C was actually called the unit interval. And if you did this in pre-calculus, what's the unit interval? You know, you go on the number line, you start at 0, and you go to 1, and you take all the numbers in between 0 and 1. Right, and it's called C because it's also called the continuum. That's another term for it, the continuum. Right, so it looks like this. You take both points 0, 1, and you consider all the points in between them. Okay, is that finite or infinite? It's infinite. I can fit it between my two fingers like this, but it's still infinite because there's no bijection between that and a finite set. In fact, you can look at the fractions in there: 1/2, 1/3, 1/4, 1/5. There's an infinite number of them. Okay. So the question was, how do you compare these two? How do you compare these two? Is C smaller than n, or is n smaller than C? Or are they the same? What do you think? What's your intuition tell you? They're the same? What do you think? N is smaller than C. Anyone think C is smaller than n? Because in a sense, n doesn't really have a limit in size, right? If you wanted to contain n, you would need like the room. You would never have a finite room, it would be an infinite room. But C you can put in the palm of your hand. Right? That's a question. Okay, so first thing we're going to do is, remember we said that you can say something smaller than or equal to something you find in injection? So let's forget about bijections. Let's try and find an injection from one to the other. So first thing we're going to do is inject n into C. You can actually inject n into C because I can take the number 1 and map it to 1, 2 to 1/2, 3 to 1/3, 4 to 1/4. Now every element on the left, I found a home for it on the right. And those fractions, 1, 1/2, 1/3, 1/4, they all live in the unit interval 0, 1. Okay, and if you look at like the geometric, I'm more of a pictoric thinker. I guess I like to see things, visual thinker. And so this makes more sense to me. You map 1 to 1, 2 to 1/2, 3 to 1/3, 4 to 1/4. So you never run out of space because you can keep getting smaller and smaller and smaller. And so we've injected n into C. Have we covered everything in C with this map? Have we hit everything in C? No. What about all the numbers between 1 and 1/2? We didn't touch any of those. So all this shows is that n is in fact less than or equal to C. It's smaller than C. Okay. Well, what's the question? Is n equal to C? Can you actually say that these two infinities, the sizes of these sets, are the same? Okay. So the answer, we had one person had the right intuition. So Cantor's diagonalization argument in 1891, he showed that they were not equal. In fact, he showed it was impossible to actually create a bijection between n and c. And this is really for the math students who are kind of listening online. This might be harder to understand, but here's how he did it, just very quick. So if you take the continuum, the numbers from 0 to 1, and imagine that you did map them from n, from the natural numbers to them. Suppose you had a mapping. So you took the number 1 from n, and you mapped it over to this decimal. Remember, any number inside the interval 0, 1 will be some long decimal, 0.3056, whatever it is. It'll be some decimal. And in fact, that sequence of numbers is how long? It can go as long as you want. Like if you look at the fraction 1/3, what is 1/3 as a decimal? Remember? Yeah, 0.3333. It's an infinite sequence. Keeps on going. Right? So decimals in general can be any infinite sequence. So you're basically mapping 1 to a decimal, 2 to a decimal, 3 to a decimal, 4. So the argument goes like this. It says, suppose you did this. Suppose you did this successfully. You mapped each one of these numbers to a number in the continuum. Right? Then what you can do, it's kind of hard to see. I'll see if I can use my mouse here. But I can create now a number that you missed in your list. You think you've hit every single number in C? I'll find a number that you have missed. Here's how I'm going to do it. I'm going to go to the first number that you picked up here. And see that 3 up there? I'm going to look at the first digit of the number that you mapped on the first time. And I'm going to say, in my number, I'm going to choose something different than that. Okay? So instead of 3, I'm going to construct my number down here. I'm going to pick 4 for that first digit. Okay? Now for my second digit, I'm going to go to your second number and its second digit. And whatever it is, I'm going to pick a different number than that. So instead of you picked 7, and I picked 3, like this. Then I'm going to go to the third number and look at the third digit that you picked. You picked 8, I'm going to pick 9, like this. And I'm going to keep doing this on and on and on. And so what I'm going to guarantee is that number that gets chosen at the end by me is different from every single number that you picked, because I made sure it differed in one digit of each one. Okay, that might be a little tricky to understand, but for kind of the more as a scientist, maybe engineers, computer science might be easier, or the math students. But so that was the argument. So he showed that no matter how you mapped it, we can always find something which didn't map, and that proved that there's no way you could actually have a bijection between the natural numbers and this continuum. Right, and so he proved this, that n is not equal to c, and in fact n was less than c. Right? Yes, we n and c. So there was a problem with this. So he proved this. He spent 10 years, Cantor spent 10 years trying to show they were equal. N was equal to C. He just couldn't do it. And then one day he probably woke up and said, yeah, let me just try and prove that they're not equal. And he figured this out. And he figured it out pretty quickly, I think, within a year. With some amazing mathematics of that time. But there was a problem, religion. So you had all this, the church and most of the mathematicians themselves who were Christian, they had problems with this. Because they had equated infinity with a God property, like a godlike property, or God himself, right? And saying that only God is infinite. And because of that problem, because he found something higher than it, they thought he's doing something blasphemous. So you got to imagine how, as a mathematician, it must have been very difficult for him, because he's proved something mathematically with these axioms. He has axioms that he starts with, and he's proved them, and he's trying to explain it to people, and people don't want to agree with it. And so now everyone tried to kind of condemn him and criticize his proof, but his proof was mathematically sound. In the world of mathematics, it was sound, right? And so then he went into depression, and then eventually they say he died even out of that depression, went into mental illness. He died, and then 10 years later, everyone adopted it, and now it's like obvious. Now everyone does, every second-year undergrad math student does this, does this mathematics, the higher infinities. And in fact, it went worse. You can see how the kind of the religious folk really panicked, because his argument was pretty amazing. He found infinities that are higher than these infinities themselves. So the concept, the diagonalization concept we showed you, that's a simple case. You can actually generalize that. Very beautiful mathematics. It's very simple. It's like second, third year undergrad math. You can do this. You can actually create a sequence of infinities, each one higher than the next, strictly higher than the next. So you have the natural numbers, you have the continuum 0, 1, and then boom, you can go using a similar argument. You can get higher and higher, which is outside the scope of this talk, so we can't do it. But after the session, if anyone's interested, I can show you how to do this. But he created this sequence of infinities. And how long is that sequence? That's also infinite. So you had an infinite sequence of infinite sequence of infinities, and that eventually leads to a paradox. Actually, it's I think it's called Cantor's, attributed to Cantor's paradox, where there's no biggest kind of infinity. I can talk to you more about it after the session if you want. Okay. Yeah, so that's it. So this is kind of like the general introduction to infinity, mathematical infinity, and the definitions. I wanted to show one thing for the math students, but there's no math students here. Any of the new people that walked in, are you math students? No? Okay. All right. So, well, maybe people online. I'll do this really fast because it's only going to be enjoyable for the math students. If you're not a math student, this is kind of dry. It's not going to make sense. But consistency and ordering. So you know how we said that x was less than or equal to y if there was an injection from x to y? Well, and then we said, how do we say two things were equal? We said two things are equal if there's a bijection between them. So as a mathematician, you have to be able to show then that if x is less than or equal to y, and y is less than or equal to x, that should imply that x equals y. Like from a point of view of numbers, it's obvious, right? But from sets, it's not obvious because the definitions were different, right? So what you have to show is if you have an injection from x to y and an injection from y to x, then you can somehow construct a bijection between them. And so this is what the proof looks like, mathematical proof. Right? So if you're not a mathematician, you're not going to understand what this means, any of it. It's a nice proof. It's very concise. It kind of cheats, though. It has some sets, it has some set math going on in there and stuff. I won't go through it. It's outside the scope. But there's a little cheating here. The proof uses Naster-Tarski lemma, some other lemma, which means he's relying on other machinery. So what's nice is Koenig, in I think it was 1906, another mathematician, Koenig, he actually came up with a very beautiful proof of this. So I'll just go through it very quickly for the mathematicians who are listening online. So if you have two sets A and B, and you have an injection F from A to B, and you have an injection B to A, okay? The problem is they're not surjections necessarily. They don't hit everything on the other side. And you want to create now a bijection between these two, given these. So what you can do is you can start with any element in A or in B. Take any element, and you can keep applying F and G to it back and forth to get this chain of points. Right? And it'll go infinitely in one direction. And in the other direction, you can apply the inverses when they're defined. And they're not always going to be defined because they're not surjective. And so you get these kind of different chains of elements. I just copied this from the internet because it was too hard to type. So you get these different chains, one going to the left, the chains going to the left and right. And then eventually those chains will stop either in, you'll get stuck in A where you can't go backwards, or you get stuck in B and you can't go backwards, or you have an infinite on both sides. And so given these three sets, then you can set up a bijection. In the infinite sequence on both sides, you can pair them up one by one. In the other ones, when they stop in A, you can start with A, map it to the next one, go to the next one, like pair them starting from A forward and B. And I know none of you understood what I was talking about except for maybe one person. But that was just for the mathematicians online, math students online. Yeah, so that's how you do the proof. So that was an introduction to kind of a mild introduction to mathematical proof. That was a very rigorous proof, so we won't go through it. Okay, and the last thing, just to give you some context about all this. So mathematical proof in general, like we didn't do a lot of proof in here. And in fact, if there were professional mathematicians in here, even some advanced students, they could have easily poked holes in the things that I've said today because I wasn't very rigorous in things that I said. What I said was correct, I believe, but it didn't have the right amount of rigor that you really need to do definitions. There's a lot of hand waving. It's called hand waving. But normally, as a math student, you'll learn this stuff. You'll begin to learn this in the second year undergrad, through your third, fourth year undergrad, and then you finally reach a point, I guess somewhere in grad school. It takes about 2 years of grad school in your PhD where you'll reach the point where you actually know whether a proof is right or wrong. And so it's amazing. You go through 4 to 6 years of education before you can even tell that a proof is correct. You think you know what you're doing when you're an undergrad, and you argue and fight. In fact, in my undergrad, like third or fourth year in school, I remember I argued with someone for 1 hour about a proof that I had written about something, and he didn't agree with it. And we argued for an hour. 2 years later, when I had actually learned really how to prove things and tell whether proofs are right or wrong, I thought back to that discussion we had, and it was complete garbage. Both of us were talking complete nonsense the whole time. But that time, I was so sure I was right. And so like it takes that time. It takes time. When you reach that point, your professors will give you an exam. These preliminary exams, qualifiers they're called, and they'll kind of stamp on a piece of paper that yes, now this student is ready to do research because the student can now tell whether a proof is right or wrong, right? And that's like it's a important stage in a mathematician's life, in a student's life, when you reach that point where you can actually do proof, and then you start doing research on it. Okay, that was it. So thank you very much. That was the talk. And questions or comments are open if you have any. I don't know if there's any access online to questions. Okay. Any questions? Yes.
I have kids, right?
Can you start from scratch? Sorry. I was going to repeat the question, but
we're going by the fact that n is less than c, right? But I have kids, so if I tell them, hey, I have a Tic Tac or Twix bar, which I'm going to cut into small little pieces, and then I have 5, 6 different tux bars. My kids are never going to pick the, let's assume C is this one bar that I cut into pieces, and then N is the higher one with a number of bars, right?
Yeah.
So when you're using that in practical life or in real life, how is it actually applied?
Oh, that's a really good question. So I don't think it's actually applied anywhere. The concept of the continuum is not. Your candy bar example, the problem is you have an infinite number of candy bars, n, but each one of them is a continuum, right? So, but n is not, and it's actually a good point. So n is a collection of points, and that's the key. If you consider them geometrically, n is just these points. How wide is a point? 0. There's no width to a point. Whereas when you have a continuum, you actually have a width there, right? And so there's a lot more going on. But even that, what I told you is not actually true, like completely true. But I can at least fool you in this audience. If there's mathematicians, then I couldn't fool you. But like, so the concept that there's actually a width there tells you that there's like I'm not sure if he knows yet. Yes, go ahead. I can repeat it. I'll repeat the question.
Would the continuum between 0 and 2 be larger than continuum between 0 and 1?
Oh, excellent question. Question is, would the continuum between 0 and 2 be larger than the continuum between 0 and 1? What do you think? What do you think? Equal? Less? More? They're equal, yeah. You can set them equal. And the way you do it is you send each value x from 0, 1 to double its value in 0, 2. So I'll send 0 to 0, and I'll send 1 to 2, and everything in between I'll just double it. And if you do that, you'll hit every single value between them. So they're actually the same. Yeah. You can go even further. If I take a two-dimensional square, a 1 by 1 square, all the points in that square, that's actually the same number of points as the interval 0, 1. The two-dimensional is the same as the 0, 1. So to break out of that infinity, you actually have to do something more creative. Anything else? Any other questions? Yes. Well, that's a very good question, and that's an excellent question. So the infinity that I showed you today is from a set theoretical point of view. It's from set theory. Mathematicians also have infinity from an algebraic point of view. And there's also a topological point of view. That's about space, how space looks, right? So like if you think about the space, if you imagine space was not bounded, suppose space kept on going, which most physicists believe it stops, but some don't. You know, we don't believe it stops. I mean, we believe it stops. Like there's the first sky, then the second sky, and the third sky. So we believe the universe stops. But suppose it didn't stop. Then there's a topological infinity, which refers to like this outer shell of the whole thing. That whole thing becomes infinity. And then in algebra, we didn't talk about algebra. We just talked about the definitions of numbers, but what if you add two numbers, multiply, divide, subtract? That's a whole different kind of a mathematics. It's called algebra, like I said. And in there, we also have a concept of infinity. You have to define a symbol, infinity, and then you have to say how does it interoperate with all the other numbers. So you make a rule, infinity plus any other number which is not infinity is also infinity. Any infinity minus any other finite number is infinity. What's infinity plus infinity? Infinity. What's infinity minus infinity? Now you have a problem. So that's not defined. Like they leave that as undefined. Can't do it. You can't do it. No. The definition is no, you can't do it. Nope. No. If you try and define it, you can create contradictions very quickly. If you define it as 0, then I'll show you crazy things. I'll show you that 3 equals 0. Things like that. Anything else?
There's an online question.
All right.
What is the Islamic application of infinity?
There is none. Next question. I'm just kidding. That's a question for the ulama. So I'll challenge the ulama to give a talk on that some other time. In fact, the reason this topic even came up was some wonderful discussions I had with Sheikh Muhammad about infinity, and then about the definitions of infinity. And I'll just leave it to that. If you ask me that question, you can also ask me what kind of battery acid I have in my car. I have no idea. So we'll leave that to the professionals. Any other question? No? It's in the world of mathematics. In the world of mathematics, I don't know if there's actually a difference. I don't know if Muslim mathematicians took on like a Muslim side of things after Cantor. I don't know. But within mathematics, it's still abstract. I've talked to my shuyukh, starting with Sheikh Amin. Numbers are all creation, are part of creation. Allah subhanahu wa ta'ala created math. So we never viewed it as pantheistic kind of numbers are infinity is God, anything like that. It's always part of creation. Any other questions? Yes. Mm-hmm. Mm-hmm.
Was there any resolution, between him and the church, or he just kind of felt mentally ill and
Yeah, so
trying to prove himself that numbers are more infinite than God?
Yeah, that's a good question. So Koenig himself, who came up with this last proof that I did really quickly, he tried to prove right away that all this was false. Within a year.
All this being
all this
Cantor.
transfinite.
Okay.
This is called transfinite cardinal numbers, is the mathematical term. But these infinities that grow. He tried to fight and show us wrong, and then right away another mathematician showed that his proof of that was actually wrong. And then so unfortunately, I think until he died, he wasn't really the recognition for this wasn't received probably till afterwards. And now it's just kind of commonplace in mathematics. Go ahead. I did not understand the question, so I'm going to skip it.
I mean, you already know this probably, but for the audience, Cantor himself was very religious, and he always believed that this knowledge that his proof was inspired by God. He wasn't a religious person.
That's a very good point, yeah. So Sheikh Muhammad said Cantor himself was religious. He, in fact, tried to contend that the infinities were also under the control of God. He tried to do that, but it wasn't too successful. Anything else? Any questions from the ladies' side? That was easy. Somebody walked out in the middle. Okay. Jazakallah khair. Assalamu alaikum.